Welcome to statistics. In this PowerPoint presentation, I'm going to go over it's just some of the basics of statistics. We're going to delve into each of these concepts a lot deeper throughout the semester, but this is a pretty good overview of what you might expect to learn today. And statisticians do a lot of things. One of the things they do is they predict things. So let's take a look at one thing that they tried to predict back in 1936. And so what you see here is a copy of the Literary Digest. It was quite a popular magazine back in the early 1900s, and it had correctly predicted the winner of the previous 5 elections. And so it was pretty confident that it could predict who was going to win the presidential election for 1936. And in its October 31st issue, it predicted that Landon would beat Roosevelt, and he would win 370 electoral votes. And this is one of the biggest improper sampling and predictions that statisticians have ever made. They did quite a bit of polling, though, so let's take a look here. So you have to think back, what was the economic outlook in 1936? What was America going through? Well, it was going through the Great Depression, right? A lot of people were out of work, and people were in soup lines and living with family, and it wasn't a very good economic boom for the American economy, to say the least. And so who did the Literary Digest poll? Well, they had polled people who they had previous polled. So car owners, they went to the DMV and got records on who owned a car, and they mailed to the addresses car owners. Also, they looked in the phone book, and they just started calling people. Numbers wasn't their problem. They in fact mailed a lot of car owners. They would take out the phone book of towns and call every person in that town who had a phone. And then their biggest one, though, was the magazine subscribers. And so they had sent out 10 million little pamphlets inside the magazines, and 2.3 million of them were returned. And we're talking about a huge sample size. I mean, that was unheard of. I mean, when we talk about, getting a sample size later in the semester, we're going to talk about 30, 40, 50 people. They had 2.3 million people participate in this poll. And they had predicted that Landon would beat Roosevelt. Well, we all know, or we all don't remember President Landon, but we all have heard about President Roosevelt with his New Deal and Social Security and different welfare programs he came out with. So what was wrong? What was wrong with this approach? Well, again, going back to the economic outlook in America in 1936, Depression, right? Who owned cars? Who owned personal home phones? And I know that everybody now has their own smartphone. Each person in every family has their own phone. It seems like if you have a family of 4, well, there's 4 phones in that family. Well, back then, only the wealthy people had cars. Only the very, elite had phones in their homes. And if your husband or wife or mom or dad is out of work, you start cutting frivolous things like magazines. So while yes, they did get 2.3 million people to return a poll, what they were doing was they were sampling only the rich, only the elect, right? And so this was a big mess up for statisticians, because they thought, well, just if we can get the numbers, if we can get out there and get a lot of people to tell us who they're going to vote for, we could accurately predict who's going to be the next president. And so the question is, have you seen this happen in your own lifetime? Well, you have, right? Just in this last presidential election, Clinton was overwhelmingly supposed to just smash Trump, and that didn't happen. Now, Trump didn't get the electoral votes that Roosevelt did, and in fact, Roosevelt got the most ever, except for Reagan. Reagan had more, but there was more electoral votes that were available to be taken then. But Trump trumped Clinton in this past election. So this is another example of asking the wrong people the wrong questions. And we'll talk about the issues with surveys, and people that lie on surveys are just not 100% forthcoming. So while one of the jobs of statisticians is to accurately predict things, and we'll talk about prediction a lot more when we get to the chapter on correlation and regression, sometimes statisticians just miss the mark. All right, take a look at this graph. What was misleading in this graph? So take a look at the title and maybe the different colors and some of the words they're using. All right. So part of the hope of taking a statistics class is that you can start critically evaluating information presented to you in a statistical manner. Everybody loves to spew stats at you. If you listen to the radio or watch the news, there's stats all over the place. So let's start dissecting this a little bit. Okay, first off, the title, right? Massive increase in house prices this year. You never want to have a title that tells the readers or the people that are going to be looking at your statistics what to think, right? Let them come to their own conclusion on that. The scale, it should start at 0, but the scale starts around 78, 79, and it moves from 0 to 80,000 in the same amount of space as 80,000 to 81,000. The actual increase in price for these homes is only £2,000 or $2,000, which is less than just a 3% increase. And if you've been a homeowner, having a 3% increase in your home value over a year is not too unheard of, right? It is large, but it's not go out right now, get a mortgage, you get a house, you're gonna be priced out the market large. And the graph on the second bar is being 3 times the size as the first bar. So visually, what this is implying to your brain is there's a 300% increase in home prices over 1 year. Let's take a look at this graph. This is a more accurate graph. An unbiased title, right? Average house price. You could also say difference in house pricing for 1 year to the next. Look at the scale on the y-axis right here, so the up and down axis. See how the increments, 10,000, 20,000, 30, they're all spaced equally, right? And then over here again you have the years. So this definitely shows a more accurate picture of the increase. There definitely was an increase, increase of $1,000. So having this consistent interval starting at 0 shows definitely a more accurate graph. So let's get into some terms. There's going to be lots of terms and definitions and symbols in this class. And the first one we're going to talk about is statistics. And statistics is just short for any kind of statistical procedure that you're going to run. And some of the uses of statistics is to look at data, to organize, summarize, maybe come to conclusions of statistics. But there's also some goals too. Number 1, interpretation. What do these numbers mean? Because interpretation usually leads to prediction, right? And the second one is standardized procedures. And we will talk about standardized tests in this class, and IQ exams, and SATs, and GREs, and GMATs. These are all standardized tests or standardized procedures we use to figure out what rank a student is. A population is the set of all the individuals of interest in a particular study. Now they can vary in size, but usually populations are really large, thousands of people, millions of peoples. Samples on the other side is usually smaller, right? This is the set of individuals selected from that population. And what you're trying to do is you're trying to get a pretty good representative sample, because you're going to try to use that information learned from the sample to infer back to the population. Okay, so graphically here we have the beige or the lighter color circle, and this is going to be our population. So the population is just, again, this entire group of individuals that a researcher wants to study, but usually it's impractical to study an entire population. So take a look at these two pictures down here. If you want to find out the average age of humans on the earth, what you would have to do is you would have to ask every single person who is alive today, starting from the brand newest baby that has been born to Emma Martina Luigia Morano, and she was born in Italy, and she's the last recorded person to be born in the 1800s that's still living. She was born on November 29th, 1899, and so what you'd have to do is you'd have to find her, ask her how old she is, in days or years or however you want to measure it, and then go all the way down to the newest baby that was been born right now. Right now. Now, that was twins, right? So it kind of gets crazy. So maybe a more common example is just student height range at one particular campus, right? So you're going to look at this campus or this campus. So the entire population might be student body, right, an entire student body on campus, and the sample might be looking at an English 101 class or a Psych 101 class. All right, some more terms. A variable, this is a characteristic or condition that changes or has different values for different individuals, right? So in my introductory video, you saw that I have bright red hair. So a variable might be hair color, right? You may or may not have bright red hair. You might have brown hair or blonde hair, gray hair, no hair, right? So this characteristic hair color, right, can change for different individuals. And so if we're looking for average hair color or the most popular hair color for our study, the variable then would be hair color. Data, and we usually talk about collecting data or looking at the data. Data is actually plural, it's Latin. It's a measurement of observations of that specific variable. And a data set is just the collection of all the data, right? Datum is what you have. You have one singular datum, and it's a single measurement or observation. And a datum is usually referred to as a score or a raw score or symbolically as X. All right, parameter and statistics. You can remember parameters go with population because P, and statistics goes with sample, so SS, right? So you have a parameter describes an entire population. If you're looking at the entire United States population, that would be a parameter. Right, so you would give not necessarily a statistic on how many hours an average United States person watches of TV a week. You would say the parameters, right? And this information is given or derived from individuals found in that population. The statistic, on the other hand, though, is describes a sample. So if I was going to say, well, what is the average age of the people in this stats class? And that would be a statistics because you're describing a sample group of people. Okay, so you have a couple different camps in statistics. You have descriptive statistics, and that's what 3/4 of our class is going to be on. The last quarter or so of the class will be looking at inferential statistics, and so some of the goals of descriptive statistics is to summarize, organize, and simplify data, whereas inferential statistics generalizes about a population, interprets the data, kind of pulls information out that isn't necessarily written there. Right? And some of the ways you're going to see descriptive statistics is tables and graphs and averages, whereas you're going to see different displays or projection or predictions with inferential statistics. And some of the common terminology with inferential statistics will be like margin of error. Right, so you can say like this candidate is leading over this candidate 49 to 47, right, with 3% margin of error. Right? Another term is statistically significant, right, and so one class average might be higher than the other class average, but is it statistically significantly higher? And I'll show you how to find out if it meets that threshold. And so one of the ways I like to use to describe the difference between descriptive statistics and inferential statistics is a first date. So please excuse my stereotypical examples here, but if you think back, I don't know, we'll go like the 1960s or 1970s if you want to say that. Right, so over here you have Mark, and he asks Julie on a date, right? And so Mark says, let's go to a movie and dinner, and Julie says, okay. So they go on their date, and they each call their sibling when they get home. So Mark calls his brother, and Julie calls her sister. And Mark's talking to his brother, and he says, oh, yeah, didn't you have a date tonight? And Mark says, yeah, I did. And he says, oh, how'd that go? What'd you guys do? And Mark says, well, I picked her up around, I don't know, 5:30 or so. And then I asked her, was she hungry or not? She was, and I was hungry. So we went to dinner, and then we saw a movie, and it was pretty good. And his brother says, yeah, you like her? And he goes, well, yeah, I like her, and I think she likes me. And, I got a kiss on my cheek when I dropped her off at her house. So yeah, overall it was pretty good. Yeah. Now watch how that conversation changed when Julie calls her sister about the date. So Julie goes into her house, and she calls Julie, And Julie picks up the phone and says, okay, how'd it go? Tell me everything about it. And so Julie says, okay, so he picks me up at 5:30, like right on the nose, not too early, but he wasn't late either. And Julie's sister says, oh, that shows respect. Okay, and then what happened then? She's like, well, he opened the door for me. Oh, he's a gentleman, right? And then he asked me, are you hungry? And I got to pick the restaurant. And Julie's sister said, okay, how did he tip the waiter? Because you can tell a lot about a man how he tips, right? Was he rude to the wait staff? Did he leave a big tip, a medium tip? And Julie says, no, he was very nice to the waiter, and he left a pretty good tip. So, it was nice. And so Julie's sister is just over the moon right now about Mark. She's like, oh, this is so good. Yeah. Okay. And then we went to go see a movie, and we both wanted to go see the new Star Wars movie. So it was pretty exciting. And we got popcorn, and we shared, some snacks, and then we talked all the way home. And he's just so romantic and kind and funny, and they just start going off and on, right about, and they're picking apart everything that Mark did on the date. By the end of the conversation, oh my goodness, they have the colors picked out for the wedding, right? And you're like, what is going on? Okay, so question is, who's lying, right? Who's lying about how this date went? Well, the answer is neither one of them are lying, right? Mark is more the descriptive statistics. He's just the facts man, right? He summarizes, organizes, and simplifies the data. He says, I picked her up at 5:30. I asked her if she was hungry. We went to dinner. We went to a movie. I got a kiss on the cheek. Done. Whereas Julie is more the inferential statistics. Everything that Mark was doing was being logged and recorded and analyzed and filed away in Julie's brain to kind of pick apart later, right? So there's really a need for both descriptive statistics and inferential statistics. Now, where it gets a little bit hairy, though, is sometimes you can infer the wrong thing, right? Mark could be a jerk, right? But maybe he waited tables when he was in college, and so he knows you need to be kind to the waiter and you need to leave a good tip, right? So sometimes our inferring or predicting or looking into data or actions or characteristics can be spot on, and sometimes it can be completely off. Okay, so this is just a different example of that. Difference between descriptive statistics and inferential statistics. So you have, in blue there, you have teaching method A, and they had, if you're just going to use descriptive statistics, an average score of 76, and you can take a look at the histogram here. It kind of looks like a bar graph, but just the lines are pushed together, versus teaching method B only had an average score of 71, so the bulk of the scores are kind of piling up over here versus on the higher side over here. But when you transfer over to inferential statistics, you kind of start thinking about things like, well, there's a difference, right? So teaching method A had a 5-point higher average than teaching method B, and you can start making generalizations or assumptions about the different parts of the teaching. So you can say, well, I don't know, maybe the teacher was better in group A versus group B, or maybe the students were smarter, or they had more parent participation, or whatever it is. All right, let's talk about sampling error. So sampling error always occurs, and it doesn't necessarily mean that the researcher messed up or didn't do their statistical analysis correctly. It's just the amount of error that is going to naturally exist between the sample they pulled and the population parameter, or the entire data. So in this example here, we have a population of 1,000 college students, and the population parameters are that they have an average age of 21.3, average IQ of 112.5, 65% of them are female and 35% are male. So if I'm going to pull a sample, and I say the first sample has 5 students in it, Eric, Jessica, Laura, Karen, and Brian, right? And I run their statistical analysis, and I give them an IQ test and see how old they are and if they're male or female. I'm going to have an average age for these 5 in group 1 of 19.8, so less than the 21.3. Average IQ is quite a bit lower, 104.6 versus that average for the population parameter of 112.5. The gender ratio seems to be about the same, so 60% female and 40% male. Going over here to sample 2, though, you see that Tom, Kristen, Sarah, Andrew, and John, their average age was 20.4. They had higher than average IQ, 114.2, and they had the ratio for gender flipped, so 40% female, 60% male. Which sample is wrong or lying or bad. None of them. It's just depending on what kind of sample you pull, you're going to get a little bit of variation than from the population. Okay, so take a look here. A researcher is interested in the effect of amount of sleep on high school student exam scores. A group of 75 high school boys agree to participate in the study. So what we consider these boys, a statistic, a variable, a parameter, or a sample. So read it again in your head. Which one do you think it is? Okay. These group of 75 high school boys is a sample. There's more than 75 high school boys in the world, so this small group would be considered a sample. Now, how they did, right, how many hours of sleep they might have got, or how high their grades were for this exam, that would be a statistic. But these boys are considered a sample. Okay. Let's talk about different types of research methods, right? So how do researchers, psychologists, scientists, people that conduct experiments and studies, how do they go about doing it? Well, there's a couple different choices they have, right? So one is the correlational method, and all this is doing is it's looking at two variables, and they're looking at, well, how does one variable define another variable, right? So scores are measured on a second variable. The whole purpose is to decide, okay, is there a relationship? And if there is a relationship, how strong is that relationship between the two variables? Relation between height and weight, sleep and exam scores, coffee sales and temperature outside, right? These can be experimental or non-experimental studies, can both use correlational. Okay. Each variable is considered separately, right? So here we have academic performance and the time that somebody wakes up in the morning. And as you can see, with it kind of going down, right? So it looks like the earlier somebody wakes up, the higher their GPA is. Now, there's other things that are going on here than just purely causal relationships here, right? Because if this waking up truly made or truly caused your grades to go up, everybody would be getting up at like 1 o'clock in the morning, no matter if they were a morning person, a night person, if they felt terrible or not, right? But this is just correlational, meaning most people who wake up early usually get better grades. There's other things going on there, though. Maybe you are a morning person, and maybe you have to get up early and get your kids off to school, and things are going on there. So again, with correlational research, we're looking at more of the relationships between these two variables, and we have a whole chapter that we dedicate to correlation. Okay. Sometimes we can compare groups, right? So one variable, violence versus no violence, and then the second variable, aggressive behavior. So do kids that watch violent media, maybe, are they more aggressive? So again, one is not necessarily causing the other, but there's a relationship there. So correlational research can help define how strong or weak that relationship is. All right. Experimental method, right? The goal is to actually demonstrate this cause and effect relationship. If, let's see, caloric intake, right? So we're saying that somebody wants to lose weight, and manipulation of the level of one variable is determined by the experimental. So if I say, I'm going to put you on a really strict diet, and I'm going to allow you to have 1,000 calories a day, would that have you lose weight? Absolutely, right? So there's a strict cause and effect there. The less calories you eat, less you are going to weigh. Other things like this blood pressure medicine, right? If you have high blood pressure and I give you blood pressure lowering medicine, you take the medicine, your blood pressure is going to go down. There's a cause and effect relationship there. Control rules out influence of other variables, right? There's participant variables and environmental variables. If I say I have a new way of teaching how to teach kids how to read, right? I'm going to do whole word reading versus phonetic reading. Well, participant variables might be how strong or weak were these students in reading before they even started my program, right? Environmental variables might be, do their parents read to them at home? Do they have access to books at a constant basis? Are they encouraged to read? that type of stuff. Okay. Some methods of control could be random assignment of subjects. If I have a new cancer research drug I'm creating a study for, I randomly assign the people to get the placebo drug versus the actual drug. So maybe every other person that signs up for the study, half are going to go in to be the experimental condition, right? And half are going to be in the control condition. So the experimental condition is the people that get the medicine, right? So again, if I'm going to use the cancer drug, then I'm going to say, okay, well, half people are going to get the actual treatment. That's going to be my experimental condition. And those who get a placebo, that's going to be more my controlled condition. Independent variables and dependent variables. So independent variable is the variable manipulated by the researcher, right? Think I the researcher, I, V. So I, the researcher, can set whatever type of variables or manipulate these variables in any way I want to do. Going back to the weight loss one, right? If I want you to lose weight, I set the caloric intake at 1,000 calories per day. The dependent variable is how your body reacts to that, right? Your body loses weight or loses weight at a certain rate versus other people, right? So the dependent variable is the one observed to assess the effect of the treatment. Right? It's dependent because it's thought to depend on the value of that independent variable. Okay. Non-experimental or quasi-experimental methods use non-equivalent groups, right? So you might compare groups, or sometimes the researcher can't control who goes into what group, right? Ex post facto design, or anytime you look at data that's archived, right? Pre and post test, individuals measured at 2 points in time. So I might give you a pre-test at the beginning of the stats class to see what your overall knowledge of statistics is, and then at the very end I give you another post-test. Okay. True experiment, control is key, right? You have to be able to control for all the different variables that might be going on. There's a clear independent variable and dependent variable, and the purpose of doing a true experimental design is trying to state that cause and effect relationship. With non-experimental, there might not be control, right, or low control. You're not necessarily trying to say cause and effect, you're focused more on the relationships between the variables. Okay. Hypothetical constructs and operational definitions. Hypothetical constructs are things, ideas that we believe to exist, but we can't necessarily observe them, measure them directly. Intelligence, humor, cleverness, sadness, happiness, right? They are useful, these hypothetical constructs are useful in describing and explaining behavior. Sally looks happy. Sam looks stressed, right? But you can't necessarily measure happiness. I can't stick out my tongue and say, oh, I am very happy today. Or you can't run a machine across my forehead and see how depressed I am, right? You can't measure those internal attributes like the way you can external attributes. Operational definition helps us define, explain, share hypothetical constructs, right? So it identifies a measurement procedure for measuring an internal behavior, kind of like an external behavior. Okay. So let's do happiness, right? So again, a hypothetical construct is a characteristic or mechanism, an attribute or a feeling, that's assumed to exist but cannot be observed or measured directly. Okay, and an operational definition tries to help define and clarify, measure, and share this hypothetical construct, right? So it's a procedure for measuring and defining this hypothetical construct that we all assume exists, but we can't really measure it, taste it, touch it, feel it. Right? So if I was to say, what does happiness mean, right? We all believe that happiness exists. You might not be happy right now sitting here listening to a statistics PowerPoint. But I think it's pretty safe to assume that most people have felt happiness at one point in their life. So we all assume happiness to be this hypothetical construct that does exist, but you can't necessarily measure or observe it directly, right? So what would you say? Well, somebody who smiles more than 30 times a day, they might actually be manic, not happy. Right? Lower blood pressure? Maybe. Some people are just born with low blood pressure, though. Right? Maybe a little skip or a hop in their step? Yeah, but they could be are in a hurry, right? They could have a slight, slight step, right? What about speaking with like a loud voice, right? They could just be kind of a loud person. So it's almost like going down the rabbit hole after a while. Like, how do you consider happiness, right? And this gets really interesting when you ask somebody, "Oh, are you upset? You look very upset, right?" They go, "No, no, I'm fine. In fact, I'm pretty happy today." Well, it doesn't look like they're happy, right? So, psychologists, researchers, scientists, we create these things, these operational definitions to help us define and measure these hypothetical constructs. Okay, so we're going to say math anxiety, right? We've all felt anxious about taking a test, or sometimes, we're doing fine on the homework, and then we get to the quiz, it's even more challenging. So how would we operationally define math anxiety? Well, you can give a survey, right? You can say on a scale from 0 to 5, 0 being no anxiety and 5 being I'm completely stressed out, what would you self-rate your stress right now? People might circle like a 4 or a 5 or write in a 6. Right? Another way you can try to operationally define how anxious somebody is when they do math or taking a math test is monitor their physiological responses, right? Strap them to an EEG or have a pulse monitor on their finger, or figure out like their heart rate, breath rate, that kind of stuff. Right. Variables of measurement. So scores are the result of observations of variables, right? So I can have scores for participants' levels of depression. Right. My operational definition might be scores that resulted from a particular measurement procedure for each variable. So a big assessment right now for depression it's called the Beck's Depression Inventory, the BDI, sorry. And they're going to ask you certain questions like, do you feel sad most days? Is it hard for you to get out of bed? Do you not find enjoyment in doing the things that you used to like to do 1 year ago, 6 months ago, that kind of stuff. And you're going to get so many scores, right? So if you're going to say, yes, that's me, no, that's not me. And if you have a score greater than 25, then the psychiatrist is going to say, okay, you are depressed, right? That's a way to operationally define this hypothetical construct that we all agree exists, depression. Okay, discrete and categorical variables. Okay, discrete and categorical variables have separate indivisible categories. Okay, no values, no halvesies, no decimals exist between two neighboring categories, right? So some of these examples of discrete is like gender, number of siblings, number of students in this class, eye color, hair color, that type of stuff, right? So I have one sister, right? I can't have half a sister. I can't have 0.3795 sisters, right? I can have 1, I can have 2, I can have 10, right? Same thing for a number of students in this class. I can have 21 students in this class. I can have 30 people in the class. I think that's the max for most math classes is 30. I can have 7 people in the class, right, if it's like an intensive writing class, but I can't have 7.2 people in the class, right? If you're going to take an anxiety survey, they can say, well, you can circle one, no anxiety, moderate anxiety, extreme anxiety. You can't have both no anxiety and extreme anxiety at the same time, right? So you can't blend these, you can't chop these in half. Continuous variables you can. So with continuous variables, there's an infinite number of possible values in between any two observed values, right? This is your height, your weight, your exam scores, your any kind of time. That's a continuous variable. Money is usually a continuous variable, right? And it's so I can weigh 102 pounds, right? I can also weigh 103 pounds, but I can also weigh 102.5. I can weigh 102.579, right? I can keep dividing those observed values into infinite number of parts. So think time, think money, think weight, right? Exam scores, salary. All right. Real limits. Right? Real limits are the boundaries of intervals for scores measured on a continuous number line. So the real limit separating two adjacent scores is exactly halfway between the scores. So each one score, has actual two real limits, the upper real limit and the lower real limit. Okay, So let's look at the number for 150. To qualify to be in the score of 150, you could score 149.5, so that kind of rounds up, all the way until you get to 150.49999999999 or 150.5 if you want to just say it like that. Right? So the lower real limit for 150 is 149.5. The upper real limit for 150 is 150.5. The lower real limit for 14 will be 13.5. And the upper real limit for 14 would be 14.5 or 14.49999. And you know this. You know this because like whenever you're at the end of the semester and say you have a 79.864 in my class. What do you absolutely know you're going to get on your transcripts, on your final grade? You know you're going to get the B, right? Because 79.648 or whatever I said is higher than that 79.5, so it qualifies to be closer to 80, right? Think like rounding up and rounding down. Okay. So categorical, and some textbooks call it discrete variables, have separate indivisible categories. Right? There's no values between the categories. If I say, what did you have for dinner last night? Did you have pizza, Chinese, or subs? You have to pick one. Pizza. No, I had Chinese. No, I had subs, right? You can't have pizza with lo mein on top. It's gross. Weird. Don't do that. Okay. Continuous variables, though, have infinite number of possible values between the categories or increments. And the boundaries consist, again, of those upper real limits and lower real limits. All right, scales of measurement. So statisticians use different scales of measurement depending on what kind of data we're dealing with. Right? These measurement assigns individuals or events to categories. And the categories can be as simple as names, right? Male, female, employed, unemployed. I live in Mesa, you live in Tempe, right? Or they can be numerical, such as 68 inches or 175 pounds or $100,000 a year. Right? And the complete set of categories make up the scale of measurement. Okay, so let's break down these scales of measurement. You have nominal, ordinal, and a Lauren ratio. Your nominal variables, think like names. Think labels with no real numeric value. Now, you can have numbers sometimes in nominal, but we'll get to that in a second. So this could be like gender, political affiliation, what city you live in, what country you're born in, right? Mesa doesn't out-city Tempe, right? Having a blue shirt on doesn't make it more of a shirt than a red shirt, right? It's just different. So nominals is more names, categories, that kind of stuff. Ordinal, this is whenever rank comes into play, order, right? So think shirt size, small, medium, large, extra large, double extra large, right? With ordinal, you can have like your ranking class. You can be the top of the class, you can be kind of in the middle of the class, you can be last in class. You can be at the Olympics, you can take like first, second, third, gold, bronze, silver medals, that kind of stuff. Interval, this is whenever you get a little bit more specific, right? But with interval and ratio, in some textbooks and some software call interval and ratio scale, that's fine. The only big difference with interval and ratio is that ratio has that hard zero, right? So interval scales when you're measuring stuff that has like an arbitrary or like a fake zero. Right? So bank account, right? You can have negative $10 in your bank account. You can have zero. You can have $100,000 in your bank account. Right? Temperature, right? It could be 97 degrees outside. It could also be zero, probably not in Phoenix, but it could be 0 degrees outside. It could also be negative 37 degrees outside. Right? 0 degrees outside doesn't necessarily mean that there's no weather outside. It just means it's really, really cold. And ratio, just again, same thing as interval, just has that absolute 0 point exam score. Now you cannot show it for one of my exams, and I'll give you a 0. You can score an 87 on the exam, but there's not really a way you can get like a negative 13% on an exam. That's weird. If you're in a class that gives you a negative score on an exam, drop that class. That's just my own personal opinion. Height, right? I am 5 foot 0 inches tall. I was 21 inches long when I was born, right? But we can never be a negative height. Right? Same thing with weight. there's no diet out there that can make me be negative 12 pounds. It's weird, right? It doesn't work. Same thing with age. I can be 40 years old. I can be 30 years old. But I can't be negative 10 years old. Right? Or salary. If you're working for a job that at the end of the year you lost money, right? Negative 10,000, quit that job. Any kind of time, right? Time to complete a race, time to complete a exam, time to clean the bathroom, right? That's all going to be ratio because it has an absolute 0 point. All of your nominal and ordinal scales is more discrete categorical, right? And your interval ratio is more continuous variables. Okay. So let's break it down with some candy. Okay, the candies above, and they're just kind of mushed there in a big pile. You can say, well, some are chocolate and some aren't. Some have nuts, some have different colored wrapping paper. So some are like orange or blue or brown, right? Green. But there's no really out-candying another candy, right? Snickers doesn't out-candy Almond Joy. The little lollipop there doesn't out-candy Skittles. They're all candy. Right, with nominal data, again, we're just describing the items in terms of names or categories. Again, NN, nominal names. And if you speak French, a clever way to remember the scales of measurement is this black triangle, noir, right? N-O-I-R is black in French. So, okay. Working up our black noir or black triangle, right? So if I place the candies in front of me, so imagine I have these candies in front of me here. You can tell, and I'm going to say, I'm going to put the candies closest to me, right? The ones I like better, closer to me. And the ones I don't really care for, they go further and further and further away from me. You can tell a lot now about preference or order when I categorize them like this or place them on the table like this, right? Because you can tell I like Snickers bars or Three Musketeers the best. And then Twix, right? But plain M&Ms, they're chocolate, they'll do, but they come right after Baby Ruth. Like, I'm not going to go out and buy this. If someone gives it to me, I'll eat it, right? But Three Musketeers or Twix, I like that. So with ordinal data, we have order or rank, and we can describe the data with. Okay, interval ratio. Again, some textbooks, some software call interval and ratio. They slump them together and just call them scale. We break it apart. Interval data is quite similar to ratio, except for, again, ratio has real zero. That should be ratio, not ration, sorry. And now distance or variance means something. Okay, so you see how we have gaps now between here? Can you tell how much more I like Three Musketeers and Twix versus like Reese's, versus like Snickers, versus like, plain M&Ms, right? These gaps now here have real difference, right? If someone was to tell me, what's the weather like outside? And I answer them in a nominal fashion, I would say, it's winter outside. Right? Winter doesn't out-season fall. Winter isn't more of a season than summer, right? I'm answering you in a nominal fashion. How's the weather outside? And I say it's winter. Okay. When I go to ordinal, right? So I go from nominal to ordinal now, and you ask me how's the weather outside, and I say it's cool. What does cool mean, right? If I live in Phoenix, Arizona, cool might be 60 degrees, 70 degrees, right? What about cold? If I say, oh, it's really cold outside, I literally might be saying 40 degrees if I live in Phoenix, right? Because it doesn't really get down to 40 very often, right? Or if I say it's warm outside, warm might be 100 versus somebody who lives in Alaska, cold is negative 40. Cool is 0, right? So does terms like cool and hot and warm, does that give you a better idea than just saying fall, winter, spring, summer? Absolutely. But listen to the difference between say it's cold outside versus when I go from ordinal to interval, right? It is 36 degrees outside. You know exactly what the temperature is now. And that's what we're talking about with these little gaps right here, right? These gaps right here have real intent, real measurement. I love Three Musketeers. Closely behind is Twix. Right? Okay. So, and then ratio, same thing, just has that hard 0. Okay, we're going to use lots of symbols and lots of statistical notations in this class. First one is X. X is your scores, right? how many people scored on a pop quiz. I gave 5 people a pop quiz. Sally scored a 4, Susie scored a 3, Tim scored a 5, and Rebecca scored a 5, and Sammy didn't show up at all, right? Those are all their X's. It's their raw score. Okay, N, big N, is the number of scores in a population, and N, little n, is the number of scores in a sample. There is a math review if you're like, oh, I don't know, I haven't taken a math class in a while. Go to Appendix A. It's in the physical textbook and online too. Just do some math review. Kind of knock off those cobwebs a little bit and get back into that math brain of yours. Okay. Variables to scores. So sometimes you have 2 different variables. So maybe we're interested in the average weight difference between wearing clothes comparing to not wearing clothes. We get 4 women, so our N sample, right, little n, is 4. And we have variables. So variable X is with clothes and variable Y without clothes. And here's their scores. And you can tell their weight's going down. Right? And terms for here would be raw scores, or X, our data. Right? Each person has a datum. Collective data set has data. Okay? And a raw score, again, singular score is datum. Okay? This little summation sign right here looks like a fancy dancy E. It stands for summation, means add it up. Okay. Statisticians use sum more than anything else, so that summation sign is huge. And the summation is followed by a symbol or equation that defines what you have to add up or what you have to sum. And adding up or summation is done after the order of operations, in parentheses, squaring, multiplication, but before any kind of additional addition or subtraction. Right? And maybe you learned this whenever you were in grade school. Please excuse my dear Aunt Sally. You have to follow the order of operations. Anything in parentheses you do first, and then the exponents. Then you multiply or divide, summation or subtraction is remaining. Okay. So this concludes our first PowerPoint presentation. The nice thing about videos is you can go back and rewind it. Just don't make fun of my voice. And let me know if you have any questions. Remember to do your homework.